muted and your video off. I am Susan Myers, Executive Director of the Southwest Jewish Congress. We are an 11-year-old organization open to all that welcomes diversity and builds bridges throughout our community. We have expanded our outreach by joining with other nonprofits and universities to provide free educational programs. This proved to be providential because, as you know, at the beginning of 2020, we held 2 programs in person, and then COVID-19 hit, and the rest of our programs have all been through Zoom. In response to the COVID-19 pandemic, we began a humanitarian program called SWJC, Building Bridges, Feeding Heroes and Neighbors in Need. Every dollar raised for this specific program feeds a hero or a neighbor and is earmarked in a separate fund. To date, we have delivered over 4,600 meals to more than 80 locations in the Metroplex. You will find more information and a link to donate directly to this project on our website. We are funded through contributions and memberships from individuals, businesses, and corporations. And yes, that may have been a hint. Visit our website at swjc.org to pay by credit card, make checks payable to Southwest Jewish Congress, and mail them to P.O. Box 700116, Dallas, Texas 75370. Before I tell you about our upcoming programs, I want to give a huge thank you to Nelda Golden, Vice President of Programming, and our dedicated committee for their enthusiasm, creativity, and commitment in planning these programs. We always have a place for people that want to share their interests and passions with us. Contact me to find out how you can become involved. Now mark your calendar and save your dates for our upcoming program. Our next program is on February the 28th at 3 p.m. Vicki Meek, 3 Decades of Social Commentary. Ms. Meek will give us a virtual tour of her art, explaining the significance of each installation. On Thursday, March 4th at 7 p.m., we will have program 2 in our Planet, Our Future series. 2 views on the impact of climate on our youth, now and tomorrow, featuring Dr. Susan Pacheco and Mr. Aaron Lair. On Wednesday, March 17th at 7 p.m., Make Stress Your Superpower, featuring retired Army Colonel Deb Lewis. All these in registration will be on our website, to where you can join the programs, and if it's not up now, it will be shortly. Now it is my pleasure to introduce one of our co-hosts for this afternoon's program, SWJC board member, Lynn Towery. Lynn?
Thank you, Susan. Good afternoon. We want to welcome you to the opening session of Southwest Jewish Congress's 2-part program, Our Planet, Our Future, which focuses on the miscellaneous human activity threatening the life of our planet and the efforts of the world's scientific community to thwart such activity and preserve our planet's future. I and fellow Southwest Congress board member Anita Weinstein have the privilege of introducing today's honored speakers. Just a couple of quick housekeeping hints before I introduce our first speaker. Tonight's event is being recorded. The link to the program will be sent to you by email as soon as they're available for viewing. Please submit your questions for our speakers using the chat button located at the bottom of your screen. Q&A will follow the second speaker as time permits. Now let me present our first speaker, Dr. Neol Tabor, professor in the Roy M. Huffington Earth Sciences Department of Southern Methodist University, located in Dallas, Texas. The department is a small group with a good number of funded research programs. They are always looking for people to participate in research, citizen scientists, undergraduate and graduate students. Dr. Tabor grew up in Nebraska, where he spent his early years living on a farm near the confluence of the Missouri and Platte Rivers, before moving with his family to downtown Omaha for the remainder of his youth. He graduated from Omaha Central High School in 1992. He attended Evergreen State College in Olympia, Washington for his freshman year of college, where he enrolled in a course named Rocks, Water, and Chemistry. At the end of his freshman year, he decided to move back to Nebraska to finish his studies. His father flew out to pack up his dorm room and drive back home with him in his 1973 Chevy Fleet-side pickup truck. Along the way, they stopped at national and state parks, and it was during this trip Dr. Tabor realized that he had learned a lot about the Earth during that freshman year, and it was the first time he recognized how enlightening his education could truly be. He enrolled as a geology major during his sophomore year at the University of Nebraska, Lincoln, and never looked back. After graduating from the University of Nebraska, Lincoln, Dr. Tabor went on to study at the University of California, Davis, where he completed his master's and PhD degrees. After completing his PhD in 2002, he moved to Dallas to Southern Methodist University as a postdoctoral researcher and then assistant, associate, and now full professor. Professor Tabor's, excuse me, I'm so sorry I messed it up. Tabor's work probes the chemistry of the modern world as well as the geochemistry of the ancient world through the study of rocks and fossils. His work has been funded by the National Science Foundation grants and has contributed substantially towards understanding carbon dioxide concentrations in the atmosphere and the relationship to global climate change over the past approximately 440 million years. During his tenure at SMU, Dr. Tabor has traveled to 6 of the 7 continents, where he collects rocks to bring back to his lab to analyze for their chemical composition. The importance of analyzing their chemical contribution is to gain insight into the conditions in which they formed, such as temperature, atmospheric carbon dioxide, and rainfall. Dr. Tabor is interested in understanding soil, its composition, and chemistry, and how those things respond to and are influenced by the environments in which they form. Dr. Tabor enjoys spending time with his wife and 2 boys, aged 12 and 14, and traveling to see new things and understanding why things in the natural world have come to be as they are. In his most enjoyable moments, Neol likes to fish, ride bikes, walk, and watch collegiate football. His most enjoyable moments are while he works in his laboratory or when he stands outdoors surrounded in silence. Welcome, Dr. Tabor.
Well, thank you very much. That's a nice introduction. Hello, everyone. I'm going to go into share screen and begin talking. So just before I go to a PowerPoint presentation that I have for you all, I enjoy watching this clock. There are all kinds of clocks in the world, and anything that changes with time, we can put a clock on it. We can measure it in terms of how it changes with time. And there's something called the World Population Clock. And what this represents is our best estimate for the number of human beings or souls that are on the planet right now. And currently we have about 7.74 billion souls among us. So let's keep that in mind, 7.74 billion, 135 million, 519, wait, 7,740,135,535 people. That's a lot of people. So let me go to my talk now, and we'll talk about humanity and climate change. All right, are you guys seeing this all right? Okay, great. So the title of my part of today's presentation is Climate Change in the 21st Century, a Consequence of Humans as a Geologic Force. So there's a lot of debate about whether there's climate change, and everybody says climate change is happens all the time. That's just part of being on the earth, is that climate will change. However, what we're usually concerned about when we talk about climate change in modern times is that humans are a geologic force. We can collectively do awesome and amazing things. And as a result, we can put ourselves in a position, the unique position of understanding that we're doing something that has negative effects, and we're going to have to deal with those negative effects eventually. And we're beginning to see evidence of how climate change is really playing out in the world around us. Shown here are the famous snows of Mount Kilimanjaro on the left-hand side. And this picture, this photograph was taken around 1980. And there were pretty extensive glaciers on the top of Mount Kilimanjaro, which is in the tropics, right on the border between Tanzania and Kenya. This is how it looked in the past few years. It has lost the vast majority of its ice cover. And by and large, what that means is that it's been warmer and that there's been less precipitation as snowfall and freezing conditions. So we're at those extreme environments, those edges of the places where we occupy, we're beginning to see evidence that they're changing, and they're responding to climate and climate change. So how does that happen? Well, I'll talk a little bit about the way we think it happens, and we know that there are factors that are involved, and I'll identify them specifically. So Earth as a system, like a good system is a balanced system, unless you like lots of change. At a balance, basically Earth receives at the surface, almost all the energy that it receives is external. Most of the energy comes from the sun to our planet and then is re-radiated out. And in a good balanced system, about essentially as much energy that comes in is used for different things on the planet. Plants can grow, winds can move matter around, and it's used to cycle through things near Earth's surface. And then that heat, all that heat that came in this minute, eventually is re-released in another minute, so that we have this nice balance of what comes in goes out. We're not accumulating energy, because if we accumulate energy, then things will warm up. One of the things that is unique about the planet Earth, compared to any other planet that we're aware of yet, is that we have an additional form of energy, energy storage on our planet. And that is through a process. It's the most complicated reaction that we're aware of on any planet. I was going to say in the universe, but that's kind of arrogant. But at least on our planet, it's called photosynthesis. And plants are able to take sunlight and combine it with the gas carbon dioxide in the atmosphere and water, and induce, it's called an oxidation reduction reaction, to produce glucose and oxygen. So glucose is important because, and it just took these things that aren't, I mean, we can't really process any of this. We use water, but carbon dioxide is worthless, and sunlight, you can't eat sunlight. But these plants are able to use a process by taking those things and making sugar. And sugar is like biological money. You can do things with it. If you take in glucose, your muscles will move, your brain will work. So there's an amazing amount of energy that is transferred into glucose in this process. And it releases oxygen, which is good for us because we're heterotrophs. We run this reaction in reverse. We take glucose and breathe oxygen, and we combust organic matter. That means turn it into gases and release energy. To release, we don't release sunlight. We release different types of energy, chemical energies and physical heat energy, as well as carbon dioxide and water. So the reverse reaction is called combustion. And you can see the massive amount of energy and power that our planet is able to accumulate from exterior sources, that is the sun. When we see things like a wildfire, we were plagued by wildfires in the American West this past summer. And all of that is energy that was stored, taken from the sun, stored in biological materials, and is now being re-released as heat energy and carbon dioxide. So this is just the tip of the iceberg of the amount of organic matter that our planet has accumulated through time. So we've kind of got like this reservoir, or a savings plan of organic matter that's been buried in the geological record, which has given us an opportunity to use combustion as a way of getting out a lot of work, getting a lot of energy for cheap. So humanity and fuels and humanity and fire are by and large inseparable. You can basically identify the origin of humanity at about the time when we controlled fire, and so controlled combustion. The earliest evidence, so humans were using fire early on, at least by 200 or pretty close to 200,000 years ago. The earliest evidence of like higher types of trade, of more potent types of energies, goes back to during the Egyptian Empire, about 4,500 years ago. There was a trade route that was set up to deliver asphalt from the Dead Sea region over to the Egyptian Empire, and that was used as a burning source. But also, if you heat up asphalt, it has different properties, and it was used as lubricants for parts of their war machines. Oops, I'm sorry. Flashing forward several thousand years into Europe and those areas, men and women discovered that there are certain types of rocks, coal was the name that we use in English, that if they're mined out of the earth, they can be used as a really clean and strong energy source. You can burn it and get a lot of energy out of it compared to wood. And so a whole industry was set up of men and women climbing into the insides of mountains, filling up carts and bringing it out, and using those to produce great amounts of energy through the process of this reaction called combustion. You just add fire. And later on, we went from these small operations to modern day, where these men are doing the same thing that these men are doing, but this is a strip mine operation where hundreds of thousands of tons are being removed every day. 150 years ago, 1,000 tons would be an amazing amount to generate in one day. So we've amped up our total coal harvesting, and as time went by, we started to look for more important or better burning fuels. And so part of what made the history of Texas, or why Texas is the way it is today, is because of what's called Spindletop. It was an area that had some of the earliest major productions of petroleum. And here's a picture of fat cats standing around and watching the money pour out of Spindletop. And finally, all the way to today, with new engineering innovations, we're able to take gas that's in the subsurface of the earth, preserved alongside these petroleum resources, take it to the surface and then liquefy it and transport it to different places. And it has the highest energy. We get more energy per volume from liquid natural gas than any of these other types. So we've innovated through time to find better and better fuel sources. And this is important because we have resource limits. So this is a graph that shows energy use by humans in percentages versus years AD, from 1800 to 2100. So it projects forward. It makes predictions about what's coming in the future. And so for most of human history, we burned wood. That was really all we had, wood or dung, to be able to have fire and energy output. By around 1850, the internal combustion engine and other engineering innovations required another type of source, a more energetic combustion reaction. And that's when coal took over. And it reached its apex right before World War I. And then as we were ramping up for war machines and massive transportation, oil started to come online, because that's an even more effective energy. And we hit the peak of oil production, what's called the Hubbard Curve, somewhere between 1970 and 1990. We're not sure exactly where we hit it, but we can pretty much anticipate that the oil that we have available to us to extract is going to be less and less than what it was last year on average. And now we're being replaced by natural gas. And there are projections here that will peak out at natural gas around 2050. And then these other options are coming online, which show solar fusion and nuclear. And the next speaker, my colleague, will be talking about some of the potential solutions that may come up that permit us to sidestep these combustion reactions. Now, here's that image of the balanced Earth again. As much energy is coming in from the sun as is being released. So we get a nice warming and a nice cooling, and it's a nice conveyor belt of energy. Now, put a factory right here with smokestacks and everything, and it's burning coal or burning natural gas, and it's releasing carbon dioxide and releasing energy, that reversible reaction where energy is released that initially was photonic energy or sunlight energy, and now it's being released as physical heat, sensible heat, as well as carbon dioxide. So the implications for carbon dioxide are important because of the way that energy moves across the universe, and in particular from the sun into our atmosphere, onto our planet, and then back out. Now, all problems really come down to energy, because everything is energy. Matter is energy. Energy moves in waves. That's the best way we can describe it, is that it's a waveform. And all of these waveforms are emitted from cosmic bodies. So like right now, I can see you, and I can see the part of you that is emitted that is visible, but you are also releasing heat in the infrared end of things. I can't see that part. However, if you've ever seen the movie Predator, it's a movie about an alien that comes to Earth and starts hunting humans for sport. And he's from a different planet. There's no reason why he would have eyes that would work on this planet. And so he has these, basically a spectrometer that's on his head. And it's wired to his neurons to let him know what the emissions are, what are called the black body emissions, seeing the things that we can't see. And so what's shown here is the spectrum of energies. And this is the only part that we can see, that we can sense readily. But there's tons of energy all around us that is not sensible by our eyes. But if we put that spectrometer on our heads, like the alien and Predator, we would be able to see into the infrared and the ultraviolet and the X-ray. And all that energy is there, we just don't see it. And so we have this, these are called black body emissions. And that's important because there's a black body story to Earth that is related to the greenhouse warming. Now, imagine putting that spectrometer on your head and trying to look at the distribution of energies that you see over the spectrum here. So this is a graph that shows spectral irradiance. Just think of it as energy, the amount of energy that's released, versus the wavelength of that energy. So all across here, this part. So there's a lot of energy that's released from our sun around the 500 nanometer wavelength, and much less out here around 1500 to 2000. The gray line represents, we can calculate that just based on its temperature. It's called the 5250 degrees C black body spectrum. This is what we calculate the the sun to emit at that temperature, because we think the sun's surface temperature is about that. Now, we send a satellite up with that spectrometer over its eyes, and it turns and looks directly at the sun. And the spectrum that it sees is shown in yellow. Not a bad match, not perfect, but it's a pretty good match. So this is what we actually see for the distribution. The highest distribution of energy is around 400 nanometers from the sun. Now we take that, we go out of space, take the satellite down, put the spectrometer on our eyeballs, and we look up through the atmosphere, looking back up at the sun. And this is the spectrum that we see of the sun at sea level. So what this is showing is that, first of all, there's a lot of energy that's absorbed by the atmosphere as sunlight is passing through it, because at sea level, we see only this much, whereas this is what's at the top of the atmosphere. So it's getting absorbed. And there are these important large departures in the spectrum at sea level that are that represent oxygen, water vapor, and carbon dioxide, these greenhouse gases that are in the atmosphere, and they capture some of that sunlight energy and excite electrons within the bonds and the molecules that they're holding and retain them there for a while before they're eventually re-released into the atmosphere and sent back out into outer space. But it's that momentary capture and holding it in place that is problematic for us. Now, having ozone and oxygen, water, these are all things that we need on our planet for it to keep going the way that it does. Carbon dioxide, on the other hand, is a problematic one because we know we're producing excess amounts of carbon dioxide, and there's a fair amount of the spectrum that still remains to be absorbed. So what that means is as we increase atmospheric carbon dioxide levels, it will necessarily result in a warming of our atmosphere and Earth's near surface conditions. So here's a plot that shows world population in billions, shown along here, and years before present. Actually, well, modern and then years before present. And so we were bebopping around, staying well below a billion for most of human history. And then once we hit the Industrial Revolution, we're clipping along and we're at this amazing rate of increase in population. This is a problematic issue because we need to build an energy system that has enough, that is accessible to modern humans. So we're always working to increase the energy output. And by increasing the energy output, that allows us to have more humans, and we're in this cycle of trying to feed ourselves with energy. And this is that same plot. This is a relative scale on the y-axis versus time. And it's showing a number of different things that we need to consider with projections for what's going on into the future towards the year 2100. Pollution will continue to increase until about 2040, 2050. Population will continue to increase until about 2060. The birth rate is going to go down and then it's going to skyrocket. And at the same time, our population, our population is going down. So our overall age will go down and our food per capita will go down and our total resources will go down. So we'll have a bunch of 20-year-olds. We'll have like 14 billion 20-year-olds without sufficient resources. And this is if we keep going in this direction. So we need to find another energy source and a series of energy sources to help us to facilitate our growing population while we're trying to figure out what to do with the population. So that emission of CO2 has a big impact beyond just population. However, this is another plot showing the population of humanity in millions. So each one of these is a billion versus atmospheric carbon dioxide concentrations in the atmosphere. So concentrations are higher over here, concentrations are lower over here. There is a strong first order parametric correlation that basically means, those are all fancy words, that means that there's no debating that human population has a strong relationship with the concentration of CO2 in the atmosphere. And we are certain that part of that parametric correlation of increasing human population and increasing atmospheric CO2 is increased combustion reactions, where we're burning these fuels that are in the subsurface. Now, what are the practical outcomes of that, and why should we worry about CO2 specifically? Well, if we have CO2 increasing and it increases the temperature of the atmosphere, that leads to the breakdown of ice sheets or the melting of ice sheets like in Greenland and Antarctica, which can raise sea level to quite a bit, hundreds of meters. This is a modest sea level rise that will take place, that could take place over a series of centuries of 60 meters. And this is what North America would look like, our home. And there are major population belts here which will be displaced. So a great deal of work will have to be done to either move these people to new places and integrate them with the pre-existing populations, or engineering these other regions that are underwater so that people can continue to live there. That's a big deal, and it's not cheap. This is a prediction for atmospheric conditions, warming and weather change in the decade 2030 to 2039 compared to today. And the hot colors, the violet and red, represent drier conditions, whereas the green, blue, and very blue represent wetter conditions. And what you can see here is that there are a few areas that get wetter at higher latitudes, but within most of the population centers, we are making a significant, or we predict a significant shift towards drier conditions. Note also that these are the bread baskets of the world. This is where we grow all the food that we're feeding each other. So that doesn't mean that we can't stop feeding each other, but we're going to have to engineer agricultural systems that bring in water from elsewhere to be able to plant those crops and keep feeding people. So we have a serious engineering problem that we need to address if we keep going in this direction. And then finally, this misbalance that we're talking about with emitting CO2 and heating up the earth leads to a misbalance in our ecosystems. The trees that are growing outside of my house, I have a nice big live oak, and it's happy here. It likes these conditions. But if you make it a little drier, just a little drier, and a little warmer, it's no longer stable here. It would have to pick up its roots and move north to an environment that's more conducive to its lifestyle. But these organisms can't do that. And as a result, when they can't move fast enough in response to change, they go extinct. And these ecosystem models predict that within the next 50 years, there may be up to 1 in 3 of the known species on our planet that have gone extinct. And this is not trivial. That's a big deal because we rely on ecosystems to be stable so that we get high yields out of those ecosystems. That's the problem. That's where we stand. And it's been a great problem because we've been able to generate a huge amount of lifestyles and a huge amount of people that all have opportunities as a result of building energy systems in this way. But we can see our limits here, and it's time to pivot, and it's time to innovate again and find ways of having harmony in the world and letting people have opportunities without poisoning it or polluting it with greenhouse warming. So that's where Lilac will come in with talking about her work. But before we go over there, just very quickly, escape out of that, stop share. Let's go back. Does anybody remember what that number was? I forgot. Anyway, there's a lot more people that were born in the past. Like we have a small town of people that were born in the 20 minutes that I've been talking to you. And every 20 minutes, there's going to be another small town that we're going to have to make for them in the next 20 to 30 years. So thank you. And I think I'm supposed to now turn it over to Miss Anita Weinstein.
Good afternoon. My name is Anita Weinstein, a board member of Southwest Jewish Congress, who will introduce our next speaker from Technion. Lilac Amirav, Associate Professor at the highly regarded and world-known scientific educational institute, the Technion Israel Institute of Technology, the Technion. Technion is the oldest university in Israel, having originally been established during the Ottoman Empire, more than 35 years before the founding of the State of Israel. Since its founding in 1912, Technion has been a pioneer in technology, engineering, and science education, and is often referred to as the MIT. Technion graduates literally built the initial roadways, bridges, and waterways that eventually became the State of Israel's infrastructure. Its acknowledged leadership in the areas of science and technology supplied the foundation for Israel's reputation as the startup nation, or today the innovation nation. Technion is the world leader in critical areas as quantum engineering, stem cell research, regenerative medicine, and smart drug delivery systems. Its role has been recognized in such noted achievements as the Iron Dome, drip irrigation, desalination, and most currently, medical breakthroughs in combating the COVID-19 pandemic. Today, through the research and works of Professor Amirav, we focus on the Technion's efforts to avoid threats to our planet, such as climate change, and preserving our planet's future through renewable energy alternatives. We express our thanks to Robert Rothschild, who is here today as a longtime spokesman for the Technion, and who also arranged for Professor Amirav to address us this afternoon from Israel. Thank you, Robert. Professor Amirav received her bachelor's degree from Tel Aviv University at the age of 18. Among her many accolades are for the Technion PhD dissertation and the receipt of the prestigious Rothschild and Sarah Lee Schuff postdoctoral fellowship. After her postdoctoral research at the University of California, Berkeley, Professor Amirav joined the Schulich facility of chemistry at the Technion. In addition to her position at the Technion, Professor Amirav is affiliated with the Russell Berry Nanotechnology Institute, the Grand Technion Energy Program, and a member of ICOR, Israel Solar Fuels Consortium Center. Today, Professor Amirav will generally address the subject of climate change, present several renewable energy approaches under consideration, and discuss in detail her current research of direct solar to fuel conversion. And now I would like to present Professor Lilac Amirav.
Thank you, Anita, for this wonderful introduction. I'm going to share my screen now.
Thank you.
I'm disabled from sharing. Someone needs to make me a co-host, so okay. No, I'm still, okay.
We can see your screen now.
Yes, yes. Just close my video so we'll have better bandpass. Okay, so I'm going to start with some general thoughts. If you'll ask yourself, what are the major challenges that humanity will have to face in the next 20, 30, 50 years from now, you will likely discover that you're all compiling a similar list, okay? We can think about water. Every 2 minutes, a child in the world dies because he or she doesn't have access to clean drinking water. We can think about food. You heard Neol's amazing talk. Growing population will require further resources. We need to supply food for this growing population, right? We can talk about the environment. We can talk about poverty and terrorism and disease and education. But I will try to convince you that when we're compiling this list, we should always put energy at the top. And this for two reasons. One, energy is likely the major, most challenging problem that we will have to face for numerous reasons that I'll address in the next slide. And the second is that if we will solve the energy problem, if we will have a clean, renewable, cheap source of energy, we will be able to use that to address most other problems that are included here. We can clean water from the sea, but that requires energy. We can come up with new novel ways of raising food, but that requires energy, right? So if we have clean, renewable and cheap resource, we can handle all of these. So we already heard about the increase in population. We also need to remember that what you see here in this slide, you see areas that are completely illuminated. We can see that from space. These are not necessarily the only inhabited places, right? There are other places that do have a lot of people living in them, and we see that they're dark because they're not as mature technologically as some of the other countries. And this is changing, and it's changing rapidly. So we're facing increase in population and increase in energy demand per person. And when you combine these things together, you reach a gap of 14 terawatt between what we can produce currently and what we will require in the next 20, 30 years from now. Most of our energy comes from fossil fuels. Okay, we're talking about 85%. You've already heard these things are a finite resource. We can dig and dig, but eventually we will run out of oil, we will run out of coal, and we need to take into consideration the consequences. So just pollution, and I'll skip that 14 terawatt. When we're talking about pollution, look at how much we stopped our life because of the COVID virus, and so far 2 million died from it. Every year, year after year, it is being estimated that 7 million people die worldwide due to air pollution. Okay, and this is data from the World Health Organization. Every year. So even if we're not thinking about global warming, but of course, we've seen Neol's amazing talk about global warming, and we know that the CO2 level is directly correlated to the temperature, and you've seen it peaking, And you've heard about all the major consequences that we will face with storms and earthquakes and sea level rise and things that will be extinct, and the food chain, and that nice plot with all the beautiful colors that talked about droughts. Well, research shows that the entire Middle East will be inappropriate for human life in 27 years from now. Okay, so I'm coming from Israel, definitely bad news for me. We're talking about sandstorms and heat waves, and if such a big area will be inappropriate for human life, we can think about millions and millions of immigrants. We can think about disease that will be spreading. So this is not something that is isolated. This is not something that we can just start to consider in 20, 30 years. This is something that is happening now, specifically because when you develop a new technology, it takes about 20 years for that technology to actually be implemented in market. So if oil is going to peak in 20 years, we need to come up with an alternative technology now. If we want to stop burning coal, if we want to start burning natural gas, we need to come up with alternative techniques to energy resource and make sure that we will not need to completely drastically change the way we used to live, and we need to do that fast. So we've heard a lot of pessimistic things, and I'm gonna try to cheer things up a little bit and talk about what we can do. And so there are lots of different solutions out there for other alternative energy sources, not just fossil fuels, right? And we're all familiar with nuclear plants and wind turbines and using water power, and everything has its place. And I think that we will definitely need all of the above. But I want you to take into consideration the fact that all these things are, the potential is for 10 terawatt. I mentioned that we're facing a gap of 14 terawatt between what we currently know how to produce and what we will require. So it's still not really fulfilling everything. We will need to build a completely new power plant every single day for the next 27 years to actually address that 10 terawatt potential. So not something that we're currently doing. And I'm not talking about the waste, the radioactive waste that some people are recycling, but it's not cheap, and some people are just sticking under a mountain and hope it will never erupt. We know that things do get wrong with nuclear energy, and this is another topic to consider, but not in the scope of this talk. So yes, there are other solutions, hydroelectric, and the potential is about 4.6 terawatt gross. What we can actually access now with current available technology is only 1.6 terawatt. There are a lot of really brilliant engineers who are working on developing new turbines that will allow us to use currents in the ocean and access wind, not just on hills, but also deep in the oceans, and making them bigger and stronger. But still, the potential that we have from wind is between 2 to 4 terawatts. So all these things are really, really important, but they will not completely solve the problem. But if we look up, the sun, that's free. That's available to everyone, regardless of the country we're coming from. And the nice thing is that the energy that comes from the sun within a single hour can supply the entire global demand for a full year. The energy that came from the sun in only 3 days is equivalent to what we have in fossil fuels, oil, coal, gas combined, okay? So definitely an amazing, amazing potential here. And what we need to do is learn how to harness it. And we're all familiar, or I expect all of you to be familiar with solar cells. So let me just say a few words on how solar cells work. So a solar cell is typically produced from a material called semiconductor. It's a family of materials that's somewhere in between metals, which conduct electricity, and insulators, which cannot conduct. And in a semiconductor, we just have a level that can have all the electrons that flow in the material, and then there's a gap, and then there's an empty level. And what happens is that if you absorb sunlight, you can kick an electron from the packed level into the empty level. And then in the empty level, that electron is free to move. So in fact, you formed an electricity. Okay, so the semiconductor absorbs light, and it translates the energy that came from sunlight into the formation of charges, electrons which are negative, and the vacancy that is being left behind, which is a positive charge, we call it a hole. So these positive and negative charges, we can now pull them, and that is electricity. And that's beautiful. And the technology that is behind solar cells is developing constantly as we speak. And we got to the point where solar cells are actually cheaper than any other energy source that you will find. They're cheaper than oil, they're cheaper than gas, but we still don't have good solutions for storage. So coupling solar panels into the grid is problematic. If we cannot store the energy, then we still depend on whether it's day or night, summer, winter. This is not something that's reliable. This is not something that we can really use at the moment more than what we see right now. So we do need to come up with alternative solutions. And as Neil already said, nature has been doing that for quite some time, right? With the photosystem, nature has been translating light that's coming from the sun, water, and CO2, and it's generating fuel. And fuel is basically a nice word for saying that the energy is stored in chemical bonds. And then if we take that fuel and we, again, burn it, which means that we couple it with oxygen, we drive the reaction in the other direction, we release the energy again. So what we need to come up is with ideas for basically achieving artificial photosynthesis. And there are a few different solutions that are being considered in the scientific community. One of the most interesting reactions to try and promote is water splitting. Because if we take water and we break it into the hydrogen and oxygen from which it is composed, we are basically producing a clean fuel. Because when you react them back, when you burn hydrogen by reacting it again with oxygen, you get water and the release of energy. And hydrogen is not a green gas. Not a gas that will contribute to the greenhouse effect. So it is clean. So how do you break water into hydrogen and oxygen? Well, one of the well-established techniques is an electrolyzer. This has been around since 1888. If you just take two electrodes and put them in water, couple them to a power supply, you run electricity through the water and you break them into hydrogen and oxygen. This is, of course, not renewable, but if we will get the electricity from a solar panel, then the electricity will be clean. And basically, we are forming hydrogen in a clean way. The problem is that we have two different steps here, right? We're converting sunlight into electricity, and that's not very efficient, and it is pricey. And then we're converting the electricity into the production of fuel. And again, this is not very efficient and is pricey. So two alternative ways are to replace the electrodes in the electrolyzer with electrodes that at least one of them is photoactive, which means that it is made of a semiconductor, kind of the same concept as we saw in the solar cells. And it will absorb light and produce charges, both of them or just one of them, and we will form the chemical reaction. These are called photoelectrochemical cells. They work okay We still need to improve the efficiency. We still need to reduce the price, but it seems, based on the analysis of the energy department, the DOE, that it is still more complicated and pricey in terms of its potential than just moving to photocatalysis. And what is photocatalysis? In photocatalysis, we're basically just taking those semiconductors and we're using particles of the semiconductors and we're coupling them to a metal. And in short, you take the two electrodes, the ones that are producing the hydrogen, the one that is producing the oxygen, and you're just coupling them in a short circuit. And we're making all of the reaction on those particles. And these are suspended in solution, so that is a very simple and cheap solution. We're just not there yet in terms of the research. But in the concept is very simple. We have the semiconductor, it absorbs light that's coming from the sun, and we make an electron jump from the full band into the empty band. So just like in a solar cell, we produce charges, negative charges and positive charges. The negative charges go into a metal, and there they can promote the reduction reaction, which means that we're breaking water and producing hydrogen, and the positive charges are promoting what is called oxidation reaction, so they form oxygen from water. So we complete this cycle. Now, both of these reactions have to occur simultaneously. You cannot use the negative charges without using the positive charges, and vice versa. And this is something that's very important to remember for later on in my talk. So what type of reactions we can produce with photocatalysis? I mentioned water splitting, but it is not the only reaction. We can think about using photocatalysis for CO2 reduction. This means that we will take CO2 from the atmosphere and combine it with hydrogen, with water, and basically form many different chemicals that can serve as fuels. When we will burn these fuels, for example, methanol, we will still release CO2, but this is called carbon neutral cycle because we took the CO2 from the atmosphere and then we release it back when we burn the fuel that we produced. We can think about other reactions that can be interesting, for example, reacting nitrogen with hydrogen to form ammonia. This is a very energy consuming reaction, and we use ammonia for agriculture. So I just want to say that this is a very general field, and water splitting is just a really critical example, but we're not limited to that reaction. People have been really interested in hydrogen because we can use it for energy. We can use hydrogen in fuel cells. So in a fuel cell, you basically react it with the oxygen and you release the energy again. And we can use hydrogen for many other industries. I mentioned ammonia, but there are many other things. So hydrogen is a really important chemical resource. And there are already trains in Germany that operate based on hydrogen fuel cells. So the technology is already out there. We just need to know how to make. So I'm simple on paper, right? Just take a semiconductor and we couple it with a metal and we can drive the reactions that we need. The problem is that the semiconductor that can perform that it needs to address quite a few requirements. That gap between the bands that I described needs to be very specific, because that will define the energy that is being absorbed from the sun and the energy that the charges then have in order to promote the chemical reactions. And we want a material that will be stable, and we want a material that will not be dangerous for us, and we want a material that will be cheap. And all these things are just hard to find. And I'm gonna go through different slides that show you lots and lots of examples of things that were examined in the literature, and just trust me, people have been working on this for 4 decades worldwide. They really looked at almost every type of a composition that they can think of, but they didn't find something that actually works. And I think that it's because the research was a little bit empirical, meaning try and error. They thought about a material, they made it, they tested the activity. They couldn't really control the synthesis or understand the correlation between the material and its activity until recently. And now we're coming in coupling the field of photocatalysis with another field, which is nanoscience and nanotechnology. And in this field, we can produce a gallery of different semiconductors and metals and metal oxides, and we can control the shape and we can control the size. And what's interesting is that on that tiny little scale, nano, okay, 10 to the -9, the material is somewhere between atoms and bulk, and the properties of the material start to change with respect to its size. So all these beautiful colors that you see here, the red, orange, yellow, green, blue, purple, they're all made of the same material. And just by changing the size of the particles, we change that very, very critical aspect of the material, that gap between the levels, the one that determines what type of light we will absorb and what type of energy we will give the charge carriers that are formed, what kind of reactions we will be able to perform with the material. So this really critical aspect is being changed here just by changing the size of the particle. And the synthesis that we're using is classical, old-style, old-fashioned chemistry, okay? We're just mixing a bunch of materials in a flask and heating them up, kind of like cooking. Very simple, something that is easy for scaling up. You can already buy TVs that are made with quantum dots, that are made with such tiny little particles. So I feel that I'm a very lucky kid that has the best Lego set ever. But if you ever played with Lego, you know that you don't just scatter the building blocks on the carpet and enjoy the variety of colors and shapes, right? You want to build something. So that's what my group likes to do. We don't just make prisms of gold and cubes of silver and hollow particles. We want to make things. We want to make complicated shapes where we connect one material to another, but we don't just control the building blocks, the sizes and shapes, but also how they connect to each other. So we design a sophisticated structure on the nanoscale where the individual building blocks and the overall morphology are meant to manipulate the charge carriers and make them move to where we want them to be. So what my lab is doing, we're designing structures, then we go ahead and we make them, and then we characterize the efficiency, and we're trying to constantly understand the fundamentals behind the mechanism of the reaction and improve our design so that eventually we will make a material that can actually address the solar to fuel conversion challenge. So just an example for a material that we developed. If you'll remember in my cartoon, we had a semiconductor and it was coupled to a metal. That's because the negative charges, the electrons, need to go into the metal. What happens is that negative is attracted to the positive. And if the negative charges and the positive charges will stay on the semiconductor, they will recombine and we will lose the energy. So we constantly need to find ways for improving the separation between the charges. So people thought that if you'll couple the semiconductor with the metal, the negative charges will go into the metal and you'll have a good charge separation. And it turns out that you form a charge separation, but it's just not lasting. The electrons go back. So a structure that I designed is one where we have two semiconductors and the negative charges go into the metal, but the positive charges go into the green particle here, it's cadmium selenide. And so now we have charge separation over 3 materials rather than 2, so we have better charge separation. And so that's just an example for the type of things that we play with. And you can see a TM image of those particles. Every single dot here that you see, that's a column of atoms. So they're really small and we have really strong characterization capabilities in the Technion. And we can start to understand how the size of the cadmium selenide or the length of the cadmium sulfide rod or the type of metal that we use and the size of metal, all these aspects, what we put on the surface and all the different features, we can start to understand how they affect activity, because we have a level of control over the synthesis that was not accessible before. And so we can isolate these parameters and conduct systematic research. And all this systematic research paid off, because when I started the project, we got just 0.5% for light conversion to hydrogen. And just a few years back, we reached a world record with a perfect 100% light to hydrogen conversion. Now, this is still not solving the energy crisis, because what I'm talking here is about the conversion of light to just the half reaction, just the part where we split water into forming hydrogen, the utilization of the negative charges, but the utilization of the positive charges, that is still a challenge. So we're still using something that's called Hall scavengers, meaning we're adding a chemical into the solution that artificially takes the positive charges instead of oxidizing water. So we're only deriving half of the reaction, not the complete cycle. So this is still not solar to fuel production. But the fact that we got 100% told us that all the systematic research paid off. It told us that all the lights split the charges, that all the negative charges reach the metal, and so on. So we learned a lot about the system. And now we're trying to implement all these insights and understanding, moving on to the missing half reaction.
Professor Amirav?
Yes.
I am sorry to interrupt you, but we need you to wrap up so we can have time for a couple of questions.
2 more minutes.
Okay.
So I just wanted to show that this is really, really, really simple. You just put the particles in water, you don't see the particles, but when you shine light, you see a lot of hydrogen. And so what my lab is trying to do now is come up with solutions for harnessing the positive charges. The problem is that the material that we're using just reacts with the positive charges and it dissolves. So we're trying numerous solutions, and obviously this is not a true scientific talk, so I will not dive into details, but we're trying different solutions to address that second component. And the good news is that we do have some success. And I will just focus on one example. We found that we don't necessarily have to split water. We can use the positive charges to address other reactions that could be of interest. For example, you can see here a reaction that produces something that the chemical industry can use. And this whole reaction for producing hydrogen and oxidizing that chemical is what we call uphill reaction. So we're actually using the energy that's coming from the light, from the sun. And we reached a nice record. That's a new world record for solar to fuel conversion, 4.2%. This is still not what we need in order to make it a practical solution. The DOE calculated that for a photocatalytic process, we need somewhere between 5 to 10%, but you see that we're getting really close to it. So I think that with just a little further push, we will get there. And with that, I would like to conclude. I hope that I convince you that there are solutions, but I do want you to be a little bit more conscious about your actions and what you do at home and how you use your energy, because the technology is still not there, and we cannot rely on research to come up and save the day, at least not on the time scale that we're facing. So if we can minimize our energy consumption and be a little bit more conscious of our actions, that is really, really critical from every single one of us. And thank you for the people who actually did the work in the lab. And I think that's time for Q&A.
Thank you. Anita, did you want to start?
Anita, you're on mute.
Dr. Amirav, please stop sharing your screen now.
Yep.
and pull your video up.
Okay.
Sorry that I took a little bit more time, but that's how we are scientists. We get excited about our science.
That was all great. I loved it.
Thank you.
Thank you.
Thank you. Does Israel have any offshore or tidal energy projects?
Currently, we only have natural gas offshore, exactly in front of my hometown. So, no, we are gonna put some wind turbines in the north, and we are trying to use more and more solar cells. But I don't think that we're working on it as hard as we should, specifically not considering the fact that we are a very, very sunny country.
Thank you. Thank you. The next one, at the end, Dr. Tabor, you can start with this, and then Lilac, if you'd like to jump in after him. At the end of World War II, there were no nuclear power plants, no wind farms, and no solar panels available for energy production. With strong government support, large capital investment, and intense research, all these forms of energy production became available. What do you see for possible new sources of energy production, such as fusion, becoming available in the future with the same type of support?
Okay, well, that's the several $1 trillion question, right? I think, yes, when I showed those graphs that were depicting the major types of fuel sources that we've utilized through time, what you saw was, what you really were seeing was innovation. And it was a major innovation to go from burning wood to going inside of mountains to pull out rocks that would provide us with energy, just the way going deep into the earth to extract billions of gallons of petroleum and gas. These are all technological innovations. And we're at this point now where those technological innovations have served us very well, but we're smart enough to realize that we're really approaching our limits. And if we want to maintain a lifestyle that provides opportunity for our children, we need to find other fuel sources. And so there was, going back to your original part of the question, there was an immense amount of government support for finding oil across the planet. Governments everywhere were involved in supporting that notion. And then businesses took over and money was made off of the speculation of it. We are doing the same today, where intermittently, where our government, for example, is putting money into alternative fuel sources, and we're seeing transformations take place. Whether or not we can, I think from my perspective, the major challenge we will have is, as a democracy, is convincing each generation of voters, each time they vote, that alternative fuel sources need to be near the top of the list of the things that we fund for original research. And the type of stuff that Lilac has presented today, these are true innovations. This is like the beginning of chipping into the mountain and finding the rocks that will give you the energy you need. But it's a much more systematic and precise approach to finding the energy that's available to us. It's a great question. I wish I could say that that I know how it's going to work out. I'm done.
I want to add a few things. I think that Neil really pinpointed the key aspects. When a technology is just being developed, it is often a little bit more pricey than competing technologies. And so when solar cells were developed, they were more expensive than oil. But that is because oil was not really calculating the true costs. So, you know, the people who die from air pollution, the environmental damage that it's causing. And so when people started understanding that there are these added costs and that they should also be, states like California started to basically encourage people to use solar cells and different financial support for it, then the industry got a big boost. And now the price of solar cells is actually cheaper than the price of oil. So I think that definitely at a certain point, we need to understand that there is a problem and we need to spend money
Right. We are, in fact, I'll just jump in. We are in
Thank you.
a very unique position of
on research, fundamental research. Sometimes curiosity is money that needs to go into universities, new technologies or something. Okay, and then when solutions are being developed, then the government needs to help them move into the market in a smooth way.
right. Innovation is going to be key, and embracing innovation. The trouble I've seen in our country in my lifetime is that there's a tendency to try and adhere to tradition, and we frequently call that conservative. But no, it's time to really embrace innovation and reward it, because that's really what we're needing now.
Okay. Thank you. For any other questions, if you have some, please email them to us. We're limited on time. Anita?
We would like to thank both Professor Amirav and Dr. Tabor for taking the time to speak with us today. In addition, we also want to thank you, our attendees, for attending our event. We hope you will join us for the second part of the series on Thursday, March 4th, 2021 at 7 p.m. via Zoom. Please check your email for a reminder or check out our website, which includes Southwest Jewish Congress, future programs, and more. Y'all have a good afternoon, and thank you again.
Thanks, everyone.
It's been my pleasure. Thank you.